So, now let us sort of visualize this. Okay. So, let us say this is my Fermi level EF, and this dotted line that you see. Okay. So, this dotted line is your Fermi function. So, this is my Fermi function, that is f of E. Now, at E equal to EF, it takes a value of half, okay, and below this it starts to approach the value of 1, and above that it starts to approach the value of 0. So, that is your Fermi function. So, that is the probability that an electron occupies the energy level. This line here, this solid line here which I mark in red, is the density of states. So, that is the density of states in the conduction band, which varies as the square root of E minus E c, and this is the density of states in the valence band, which varies as the square root of E v minus E. Okay. So, these are the number of states available, and that is the probability that these states are occupied, and the product of these two essentially gives you the electron count in the conduction band and the hole count in the valence band. So, the product is given by this region which I am shading here. So, you see that the density of states is large, right at this point the density of states is 0. The Fermi level, the Fermi f of E is not 0, but it is 0 times some non-zero value which is essentially 0. So, you have 0 electrons here, but as we just move away from this point, as E goes greater than E c, square root of E minus E c is no longer 0. So, you do have some density of state, and you have the maximum possible Fermi level, Fermi f of E value, the maximum possible value of f of E, sorry, not the Fermi level, the maximum possible value of f of E, and therefore, the product begins to take a significantly large number, and therefore, you will find that the electron count increases. But then as you move further up, the density of states goes up, but the probability of occupancy comes down, and therefore, the electron count starts to fall off. So, you find that the electron distribution in energy above the conduction band edge looks like what is shown in this shaded region here. Similarly, if you look at the whole population or the whole count in the valence band edge, you have the same story. Here you have the density of states being 0, okay, and 1 minus f of E, which is basically this gap being non-zero. Okay. So, we are interested in this number now, and therefore, the number of holes right at this edge is 0. But then as we start heading lower below EV, EV minus E increases, but at the same time the Fermi level starts approaching 1, which means this value, which is basically 1 minus f of E, begins to decrease. Okay. And you find that the probability keeps getting down, which allows the number of holes or the hole distribution in energy to take a shape as shown in this shaded region here. Okay. So, that is a graphical visualization of how the electrons and holes are distributed in energy. All right. So, now let us start making some definitions. Now, let us say I have a pure semiconductor, and what I mean by pure is it is not, there are no impurities present inside the semiconductor. Okay, and I am bringing this concept up in the context of something which I am going to talk about very soon, which is something called as doping. Okay. So, in a pure semiconductor, you have your valence band, you have your conduction band, and you initially had at t equal to 0, you had all the electrons being bound by all the atoms of the semiconductor lattice, and you had all the valence electrons all located in the valence band. The conduction band was largely, it was completely empty at T equal to 0. Now, as we started increasing the temperature, okay, the electrons gained some thermal energy, and some of these electrons were promoted to the conduction band. So, you started having holes or vacancies being left behind in the valence band and electrons being promoted to the conduction band. Okay. So, this was as we started increasing temperature. Now, in the case of intrinsic silicon at 300 Kelvin, you will find a count. If you look at the number of electrons per unit volume sitting in the conduction band, it would be about say 1e10 per cc. All right. So, this is what happens as you start increasing temperature, which means that the number of electrons present in the conduction band must be equal to the number of holes present in the valence band, because it is these holes are the consequence of the electron getting promoted to the conduction band. Okay. So, if you were to measure, if you were to take a carrier count of the number of electrons in the conduction band and the number of holes in the valence band, these two are equal. Okay. One has led to the other, and that concentration has got a special term for an intrinsic or a pure semiconductor, and that is something called as the intrinsic carrier concentration. Okay. And we will always denote it by the symbol Ni. Okay. So, both when I say the number of holes is equal to Ni, it means that the holes have, the whole concentration has matched the intrinsic carrier concentration, which is the semiconductor is like as though it would have been in a pure state, and all this is at the conditions which is known as thermal equilibrium, which is I have not thrown light on the semiconductor, you have not applied any voltage, you just have the semiconductor sitting in dark, sitting at a temperature, at some temperature T, and as a consequence of the temperature you applied, you have a certain statistical count, or you have a certain population of free electrons and holes, and that population is called as the intrinsic carrier concentration, which is Ni. Okay. Now, if you go back to what we looked at, what it implies is that if you have a density of states and you have a certain f of e, the product of your density of states and f of e integrated over your band edges, that is this count matches the number of electrons. So, the whole count matches the electron count, and we always talk in terms of concentration. So, N is the number of electrons per unit volume, P is the number of holes per unit volume, Ni is the intrinsic carrier concentration per unit volume. Okay. So, now we can sort of bring in some of the concepts we learnt earlier. So, we earlier found that N is equal to the effective density of states in the conduction band into e to the power minus Ec minus Ef by kT, where Ef is the Fermi level, right, and Ec is the conduction band edge. Similarly, P was equal to Nv into e to the power Ev minus Ef by kT, where Nv is the effective density of states in the valence band. Now, in an intrinsic semiconductor, N is equal to P is equal to Ni. Okay, so, which is the intrinsic carrier concentration. This means that I should be able to equate these two terms. Okay, so, what happens? So, N is equal to Ni. Okay, so, Ni is essentially that term there. P is also equal to Ni. So, P is equal to, so Ni is also equal to that term there. And if I take a product of these two equations, let us say this is equation 1 and this is equation 2, and if I multiply these two equations, I get Ni square on the left side and I get Nc Nv into e to the power Ec minus Ev, minus of Ec minus Ev. So, because you have the Ef term will cancel off, okay, and you have Nc Nv e to the power minus Ec minus Ev by kT. So, that is Ec, that is Ev, and this is Ec minus Ev, which is nothing but your energy gap. Okay. Therefore, Ni square turns out to be Nc into Nv into e to the power minus Eg by kT. Now, what is Nc? Nc is a constant, right. It only depends upon some universal constants and the effective mass of the electron. Nv is also a constant, it depends upon several universal constants and the effective mass of the hole. Eg is again, at a given temperature, Eg is a fixed parameter, right. You have the energy gap. So, which means to say that this Ni square seems to be very much a constant. As long as you do not vary Nc, Nv and Eg, you can't vary Ni square, okay. And this is a very powerful relation, because it tells you a method to count at a given temperature. If I want to know what is the intrinsic carrier concentration, it is essentially the square root of Nc Nv into e to the power minus Eg by 2 kT. So, as the energy gap increases, the Ni decreases, and that is very intuitive, because as the energy gap decreases, I need a higher temperature for me to promote my electron from the valence band to the conduction band, and therefore, my intrinsic carrier concentration decreases. So, this is a very powerful relation, it is a very helpful, a very useful relation. So, let us play around with this a little bit more. Okay. So, now let us say we have our intrinsic semiconductor. Now, when we discussed the Fermi level, we really did not locate it, okay. We just sort of vaguely drew it somewhere between Ec and Ev, we did not really locate it accurately. So, what is the accurate location of the Fermi level? So, we know Ec, we know Ev, because in a semiconductor Ec is defined by the electron affinity, okay. So, there is a certain electron affinity and that defines my Ec, and then I have my energy gap, and therefore, I know Ev with regards to Ec, okay. But where is this Fermi level located? Because the Fermi level location is important, because that is where f of E is going to take a value of half, f of E is equal to Ef is equal to half. So, what is the location of the Fermi level? So, once again let us get back to these equations. We know that n, that is the number of electrons in the conduction band, is Nc e to the power minus Ec minus Ef by kT, P is Nv e to the power Ev minus Ef by kT, and for an intrinsic semiconductor, what we do is we give that Fermi level a special name, okay. So, we want to know where is the Ef for this intrinsic semiconductor, we give it a special name and we call it the intrinsic Fermi level, okay. So, EI, or sometimes it is EFI is also used. This EI or EFI is something called as the intrinsic Fermi level, okay, and we are trying to identify its location, which is basically the Fermi level location in a pure semiconductor, okay. So, for an intrinsic semiconductor, I can replace this EF by EI, okay. So, EF we will keep it as a more general Fermi level variable, okay, and EI we will use it specially only to indicate the Fermi level of intrinsic semiconductors. So, then in that case your N for a pure semiconductor, you will find N is equal to Ni, which is Nc e to the power minus Ec minus Ei by kT. Okay, I am just replacing the variable Ef with the variable Ei, because Ei has got a special status, it is the Fermi level location for a pure semiconductor, and P is also equal to Ni, which is Nv e to the power Ev minus Ef by kT. So, that is your P, and since both these have the same value, they are both equal to Ni, you can equate the number of electrons with the number of holes, with that being the intrinsic Fermi level. And just by solving this equation, you will find that EI is equal to EC plus EV by 2 plus KT by 2 ln of NV by NC. Okay. So, what is EC plus EV by 2? It is the location exactly at the mid gap. Okay, so that is my energy gap. If I were to take a location here, it is EC plus EV by 2. Okay. And what this is saying is that you reach mid gap and you offset it by this quantity, that is KT by 2 ln of NV by NC. If you were to offset yourself from the mid gap by this amount of energy, you will find the location of the intrinsic Fermi level. So, to draw this more cleanly, the intrinsic Fermi level is not generally located right at mid gap, it is slightly offset from mid gap. So, let us say this is EC, that is EV, let us say that it is perfect mid gap EC plus EV by 2. Now, if this quantity NV by NC is a positive, is say NV is greater than NC, so which means that this quantity is a positive number, then my EI location, my Fermi level is actually located there. Okay, so that is my intrinsic Fermi level position, which means that my F of E, okay, the probability of occupancy will take a value of half at that location, at that energy. Okay. So, when does this term become equal to 0? Because if this term were to become equal to 0, then the Fermi level, the intrinsic Fermi level is located exactly at mid gap. This term will become 0 if NV is equal to NC, because then you have the logarithm of 1, which is 0. So, when does NV become equal to NC? If you look at the expressions for NV and NC, you will find that you have most of the terms to be constant, or most of the terms are universal constants, except for the effective mass of the holes and the effective mass of the electrons. So, if the effective mass of the holes matches the effective mass of the electrons, then you will find that the intrinsic Fermi level lies exactly at mid gap. Otherwise, it is going to be offset by this number, and in fact you could take this 3 by 2 and probably locate it outside the logarithm. So, you can call that 3 by 4. Okay. So, that is your expression for the location of the intrinsic Fermi level. Okay. So, now we are going to approach a different topic, okay, and we are going to call this as something called as doping, okay, and I will explain what doping means. Now, we know the location of the intrinsic Fermi level. So, you know this is EV, you know that is EC, and I know my intrinsic Fermi level location, that is EI. Okay. That is the Fermi level in a pure semiconductor. Now, I could, so the pure semiconductor implies I have my silicon lattice, right. It is so if you are going to talk about silicon, you have your silicon lattice, which each silicon atom being bonded to 4 other silicon atoms. Okay. So, if you were to look at it in a tetrahedral lattice formation, it is essentially this, it has got 4 neighbors and these have got 4 neighbors, and so on, the lattice continues that way. So, if I were to now create a defect, I get rid of the silicon atom and I bring in some other species. Okay. Now, silicon has got 4 electrons in the valence shell. I can bring in some other species that sort of forces itself to bind and accommodate itself into this lattice, but in order to do so, it could change the electron or hole population. It could either give away an electron or take away an electron. So, let us say you are going to add an impurity into the lattice, you are purposefully adding a measured impurity concentration into the lattice. Okay. And if this is all done at a suitably high temperature, which means if it is if the temperature is not 0 Kelvin, these impurities could get ionized and they could contribute or change the electron and hole population in the semiconductor. So, if the electron and hole population changes, the Fermi level location in this doped or impure semiconductor will shift away from EI. Okay. So, if this is EI, it has got a special relevance. Okay. So, it is an imaginary Fermi level to remember, because that is what your pure semiconductor looked like. We will draw it with a dotted line. Now, if you take the same semiconductor and you dope it, you are going to create impurities, and the Fermi level could take up a new position, and we will now call it EF. Okay. It is no longer EI. Okay. And EI is just this dotted imaginary line, which is no longer valid for this new semiconductor, but it gives you a reference as to how much of impurity you have added to the semiconductor. So, you could actually artificially move the Fermi level location about by adding impurities in the semiconductor. Okay. And this concept of adding impurities to the semiconductor in order to relocate the Fermi level is called as doping. Now, why will the Fermi level relocate? Firstly, because your n is equal to Nc e to the power minus, let us say in an intrinsic semiconductor, in a pure semiconductor, it was Ec minus Ei by kT. So, that was your n, which was equal to Ni. Now, I have changed n. Now, I have made n to be different from Ni. Okay. So, let us say I made n to be greater than Ni. I can't have this exponent have the same value here. Okay. So, now my EF, it will have a different value for EF, which is going to be smaller as compared to Ec minus EF. So, in general, so we will get back to the general expression which we derived, which we looked at earlier, by sort of integrating the from 0 to Ec to infinite, when we integrated the density of states into f of E into dE, we obtained this expression, and this expression had the Fermi level term in it. And for an intrinsic case, this Fermi level was the special intrinsic Fermi level, but in general we will retain this symbol EF, and increasing n will relocate EF in order to decrease this term. Decreasing n will relocate EF to increase this term, because it is e to the power minus a larger number in order to reduce n. So, if a semiconductor is doped so as to increase the electron count, you will find that this term has to decrease, or the Fermi level will move away and above the intrinsic Fermi level, and this semiconductor is called as an n type or an n doped semiconductor. The doping or the impurity was added to increase the electron count. On the other hand, if the doping or a dopant is added to increase the hole population, then it is called a p type or a p doped semiconductor. Sorry. If the dopant is added to increase the hole population, it is called a p type or a p doped semiconductor, where your EV minus EF, so this term has to increase or decrease in order to accommodate that. So, you will find that if you are trying to increase the hole population, EF will have to move below EI in order to get closer to the valence band edge. So, that is EV. Okay. So, now how do we so let us just talk about more technical terms. Okay. So, you have two kinds of doping. Okay. So, you have p type doping, where you are trying to increase the hole population and relocate the Fermi level. So, this is the intrinsic Fermi level. You are going to relocate the Fermi level to some location here, so as to bring down this value of EF minus EV. Okay. And this kind of doping was called as P doping, and it is done with something called as acceptors. Okay. So, what the concept here is that you have your silicon lattice. Okay. So, let us say we will just draw these 5 atoms, and initially each silicon atom was bonded to 4 other silicon atoms. It had a valence, it had 4 valence electrons. And now if I were to remove the silicon atom and bring in an impurity which has got only 3 electrons, okay, this impurity has got 3 electrons and it is going to participate in bonding. So, it is going to bond with 3 of the silicon atoms, but in order to bond with the 4th, it is going to take away an electron, a free electron from the lattice, and it is going to bond with the 4th silicon atom. So, it is going to complete its bonding by taking electrons away from the existing electron population, and it is going to essentially leave behind a hole. So, therefore, in some sense it has improved the hole to electron ratio. It has increased the hole count with respect to the electrons, and therefore, this dopant which accepted the electron is called as an acceptor like dopant, and this kind of doping is called a p type doping. Now, you can, depending on the concentration of dopants I have added, I can change the hole and electron population accordingly, and therefore, it is useful to define a concentration for your acceptor ions and be typically denoted by the symbol Na. Okay, so, capital Na is the number of acceptor dopants added to the intrinsic semiconductor per unit volume. So, it is always per unit volume. Okay. Now, similarly, we could add something called as donor dopants in order to create a N type semiconductor, which is you have a silicon lattice where the silicon atoms are all bonded to 4 other silicon atoms. And now I am going to bring in another species, an impurity which has got 5 electrons in the valence shell. So, we are going to bring in an impurity which has got 5 electrons, which means it is going to use up 4 electrons to bond itself, to accommodate itself into the lattice, but it has got this 5th electron that is free, and if it is ionized, this 5th electron is free to move about in the lattice. So, this has essentially increased the electron population. So, this kind of doping which increases the electron population is called an N type doping, and it is done with donor dopants, because this dopant donated an electron as opposed to accepting an electron. It is called as donor dopants, and what this does is it essentially moves the Fermi level above EI in order to decrease the EC minus EF gap and increase the electron concentration. Okay. And once again, it is useful to define a concentration for the donors, and we do it with the symbol Nd, which is the number of donor dopants per unit volume. Okay. So, what does doping actually mean? So, it means that you have added an ion. Okay. So, if this dopant is ionized, what you have essentially done is you took a neutral species as a neutral, let us say you are trying to do N type doping. You have taken a neutral species which is an atom which had 5 electrons in the valence shell and several other electrons in the inner shells, and it had some positive charge in the nuclei, and you have implanted it as a defect inside your silicon lattice. And since one of the electrons could not be used for bonding, so these 4 were used for bonding, but this electron could not be used, and at a significantly high temperature this electron got away and became a free electron in the silicon lattice. So, this is free, which means that this species now is essentially positively charged, because the charge in the nucleus is now not balanced by the electron charge cloud. So, it is fixed because it is now bonded itself to the silicon lattice. It is not a moving charge. This positive charge is now fixed, but so it is a fixed ion which has got positive charge, and it has left behind a free moving electron which has got a negative charge. Okay. So, essentially by doping the silicon atom n type, we have maintained charge neutrality for the entire system, which is the silicon is charge neutral, the dopant plus this ionized dopant plus this extra electron balances itself out in terms of charge, and the entire species charge neutral. It is not that we have charged the silicon atom, okay, it is charge neutral. All we have done is added an entity which was charge neutral and ionized it, which means we have pulled an electron away and left behind a fixed immobile positive charge. Okay. So, that is what has happened when we doped it n type. Similarly, when we doped it p type, we have not changed the charge, we have not disturbed the charge neutrality of the silicon. So, we took a neutral species which had 3 electrons and an equivalent balancing negative or positive charge inside, positive charge in the nucleus, and we added this into the silicon lattice, and this species now gained an electron, it accepted an electron in order to bond with the silicon lattice, and by accepting an electron it became an effectively negatively charged ion, because now the positive charge in the nucleus does not balance the excess negative charge on the shell. So, it became a negatively charged ion which is an immobile ion, but it left behind a positively charged mobile species called the hole. Okay. So, the hole is free to move about in the silicon lattice, and you have an ionized species here which has got a negative charge and is fixed. So, essentially what you are doing by doping is, for p type doping we are creating fixed negative charges, immobile negative ions in the silicon lattice and mobile holes added to the silicon lattice. These are mobile. And in the case of n type doping, we are creating fixed immobile positive charges and mobile electrons for the silicon lattice. So, essentially the entire system is charge neutral. Okay. Now, if all the dopants were all ionized, if everything that we added were all ionized, what is the concentration of this fixed negative charge, these negative ions in the case of p type doping? It is a Na, because we added Na acceptor like dopants per unit volume. All these Na dopants were ionized and all of them gained a negative charge. So, you have Na fixed negative charges per unit volume sitting in your p doped silicon. On the other hand, your donors, we added Nd donors per unit volume, all of them got ionized and they all became positive ionized species, and we have Nd positively charged immobile species located per unit volume in the silicon. So, that is the situation when we dope it, and clearly we are affecting the electron and hole concentration, which means we are affecting the Fermi level location. Now, it is possible to counter dope a silicon. So, you add not only Na or Nd, we add both positive and negative, we add both acceptor and donor dopants. So, this is something called as counter doping. Okay. Now, if we add both Nd and Na, but your Nd turns out to be greater than Na, then it is equivalent to you doping the semiconductor N type with an effective dopant concentration of Nd minus Na. It is like as though we have added this many donor atoms. On the other hand, if Na is greater than Nd, the semiconductor will behave like a p type with an effective dopant concentration of Na minus Nd. Now, it is possible to balance Na and Nd and make the semiconductor appear like as though it is intrinsic, and this is something called as complete compensation. So, we have completely compensated any dopant with the counter dopant. So, these things are quite useful, and it would become clearer when we do a problem session where we will solve some problems, just to calculate and get comfortable with the calculations.